systems involve reversible reactions, which are happening both in forward and backward directions at an equal rate. So this is an example here. It's written with an arrow going to each direction. The forward rate is normal direction, and then reverse is going this direction. If the system is disturbed, if there's something changes in the system, then one of the rates will temporarily increase to counteract that change. So say something was added on this side, it would shift that way, it would go faster that way just for a short time to kind of balance everything out again. But on the other hand, if nothing happens and it's undisturbed, then the concentrations of each of those chemicals will stay the same indefinitely or forever. I kind of drew an example of that down here. In a beaker, you have an equal number. You have two of each AD, AB, CD, and DC or CD on there. One of the bases for today's experiment is Le Chatelier's principle, which allows us to predict how a reaction is going to change, or how the equilibrium will shift. Le Chatelier's principle basically says if you change something in a reaction that's at equilibrium, it will then shift and change to counteract that. So I've written out a table for you that says some of the predictions. The first one, if you increase the concentration of either the product or the reactant, then the reaction will shift away from where you added it. So if you add a reactant, it will shift towards the products. If you add a product, it will shift towards the reactants because it wants to get rid of that excess of the chemical that you added. The next type is when you decrease the concentration of something, then it'll shift towards that. So if you decrease reactants, it'll shift towards reactants. Same with products. If you decrease products, it'll shift towards the products to make up for what was taken away. The next two are heat. If you increase the heat in the system, it'll shift away from the heat, or exothermic reactions are more favored because it wants to get rid of that excess heat, use it up. And then when the temperature is decreased, it will favor endothermic reactions, and it'll shift towards the heat or energy, and that's to make up for the heat that's lost. And then if you added a catalyst, which we're actually not doing today, but just for your reference, if you add a catalyst, there will be no shift because the rate of both reactions is going to increase equally. So it's not going to shift in one direction or the other because both rates are increasing. Okay. Down at the bottom here, I added just a few examples. Number one is this increased concentration one. If you have A plus B goes to AB and you added B, it will shift to the right towards AB. And then I drew a little picture. So you start out with 4 molecules of A, since A has already been added, 3B and 3AB. And then after the shift is complete, it shifts away from A, so it makes more AB. As you can see now there are 4 AB, only 3A and 2B because one of those B's was used up to make more AB. The second one is another example just like the first one, but it's decreased. If you take over the reactants, and then again I drew another little picture of that, we have only 1B, 3A, and 3AB. After it shifts to counteract that change, you have 2B, 4A, and only 2AB because one of those AB molecules was broken up as it shifted to the left. Here's an example of what we'll be doing today. Up at the top is the full reaction, and right below that is the net ionic equation there. As you can see, there's one ion that's pink and another ion that's blue. When they're in equilibrium states mixed together in a beaker, the overall solution will appear purple because it's balanced between both sides. So there's a balance between the red ions and the blue ions. And then obviously they're just given by the cobalt ion and then the cobalt copper ion. So then this is the general setup of something that will be in your worksheet, but I just want to walk you through something that happens like the AB reactions we talked about before, but using actual chemicals this time. So if we made a disturbance or change by adding hydrochloric acid, that breaks up into two ions, hydrogen obviously and chlorine. The chlorine concentration will increase. And when the chlorine concentration increases experimentally, the solution will turn more blue, so that's an observation. And then based on that, if you look back up to the reaction, if it's turning more blue, you can infer that it shifts to the right. Because it's more blue, there's more of the product being made. It's also called shifting forward. And then, as a result of the shift, which species is increased or decreased? Because you added chlorine, which is a reactant, it shifted towards the products, so it made more of the products. So the species that was changed or increased ended up being the cobalt copper chlorine, and that increased as a result of the change.
Okay, welcome to the experimental part. So in part 1 of the experiment, we are going to manipulate the chemical equilibrium by using different temperatures. So here we have 0.2 molars copper sulfate solution and saturated potassium bromide solution. So the copper solution has blue color and potassium bromide solution is colorless. Okay. So now first what we are going to do is to measure out 15 milliliters of copper sulfate solution and 5 milliliters of potassium bromide solution. And we are gonna just combine together. And then using a glass stirring rod, just gently mix it together. Alright. The final product is kind of bluish and something like a little bit greenish. So now we are going to split this solution into 3 clean glass test tubes, just as equally as possible. For the first test tube, we are gonna use it as a reference. For the second test tube, we are gonna put it into a hot water bath. So we have some water in a large beaker, and I just turn the heater on to heat it up. So we are gonna place the second test tube into the hot water bath. And then let's wait for 10 minutes. For the third test tube, we're gonna put it into the cold water bath. So we have some ice here, and in order to even cool it down, I took a piece of salt and then ground it up. So we are gonna just add it to the ice. Now we place the third test tube into the ice, the cold water bath, and we are going to wait for about 10 minutes. Now I'm going to take the second test tube from the hot water bath, and let's see the color. And I recommend doing it on the white background because it's sometimes hard to see the change of color, but the second tube should be more green than the reference. Okay. And the third test tube, which was cooled in a cold water bath, should be slightly more blue than the reference. So please record the color and explain the change of the color based on the Lesch-Tetorius principle. part 2 of the experiment, we are going to manipulate the formation of metal complex iron thiocyanate by putting the chemical species or ions into the equilibrium system. So first we have 0.1 molar of iron 3 chloride and 0.1 molar of ammonium thiocyanate and 0.1 molar of tin 2 chloride solution. And only the iron 3 chloride solution has a color of yellow, and the other solutions are colorless. Alright? The first thing that we are going to do is to measure out around 50 milliliters of DI water, and then put 20 drops of iron 3 chloride solution and 20 drops of ammonium thiocyanate solution into the beaker. Using a glass rod, just gently mix it together. As a final product, we have a solution of a dark reddish color. So the next, we are going to split this solution into 4 different clean glass test tubes. You don't have to use all of the solution. Just fill out around half the volume of each test tube. Okay, now the first test tube is going to be used as a reference. So we are going to just leave it in a test tube rack. For the second test tube, we are going to add another 20 drops of iron 3 chloride solution. For the third test tube, we're going to add another 20 drops of ammonium thiocyanate solution. For the last test tube, we're going to add tin 2 chloride solution. Now, using a glass stirring rod, we're gonna gently mix the solution together. Now, as you can see, the second test tube has a slightly darker red than the control. And third test tube also has a red color compared to the reference solution. For the fourth test tube, you see a slightly lighter color than the control. So based on the color, please predict in which direction the equilibrium shifted, and please explain the phenomena based on the Le Chatelier's principle. Okay, in the third part of the experiment, we are going to control the ionization of weak base ammonium hydroxide by adding its conjugated acid. So we have 15 molars of ammonium hydroxide solution and 2 molars of ammonium chloride solution and a phenolphthalein indicator. So all the solutions are colorless, okay? And what we are going to do first is to add 2 drops of ammonium hydroxide solution and 2 drops of phenolphthalein indicator to the beaker. So the phenolphthalein indicator shows red color when the solution is basic, and it's colorless when the solution is acidic. So we're gonna just mix it together and then split it into 2 clean test tubes. So the first test tube is going to be used as a reference, and the second test tube is for the second test tube you're going to add 2.5 milliliters of ammonium chloride solution. So we have 2.5 milliliters of the solution. So I'm going to add the solution to the second test tube. And now I'm going to gently mix it together. Now you can see after adding the ammonium chloride solution, it became colorless, right? So based on this, the color, please predict in which direction the chemical equilibrium shifted. Part 4 of this experiment, we are going to control the ionization of weak acid, acetic acid, by putting its conjugate base. So we have 2 molars of acetic acid, 2 molars of sodium acetate, and methyl orange indicator. Please note that each solution are colorless. And now we are going to put 2 drops of acetic acid to 15 milliliters of DI water. We are going to add 2 drops of methyl orange indicator. Now, just gently mix it together. So this methyl orange indicator note red solution when red color when the solution is very acidic with a pH of less than 3.2, and when the solution is more basic with a pH above 4.4, then solution will turn to yellow. And the solution will be orange when the pH is between the 2. So now I'm going to split this solution into 2 clean test tubes. So just like this previous experiment, we're gonna use the first test tube for the reference, and for the second test tube, we are going to add 5 drops of sodium acetate solution. And then we are going to gently mix it together. Now, compared to the reference, you can see the solution, the color of the solution is more yellowish after in the sodium acetate solution. So based on this observation, please predict the direction of the shift in the equilibrium. Okay, in the worksheet, you're going to first fill in the first table. In the first table, you're going to describe the color of the initial solution for each experiment. And then please describe the color of the solution after mixing them together. And then please give the ion that present the color in the mixture. Not all ion has color, right? So please only provide which ion has the color in the equilibrium mixture. In the second table, you're going to first describe the net ionic reaction for each reaction. And then in the first column, you're going to indicate what kind of experimental step you took. For example, when you heated up the solution, please describe that you put the solution in a water bath, or hot water bath, or cold water bath. And then please identify what kind of chemical component is getting involved in the procedure. For example, in this case, heat is added or removed. In the next column, please describe the color of the equilibrium mixture after applying the experimental step. And then please describe in which direction the equilibrium shifted based on the Le Chatelier's principle. And at last, please describe why the shift is brought by the experimental procedure. The second table, in the second page, is just similar, but you put the chemical species into the solution. So please describe what kind of solution you put into the mixture. But not all the chemical species or not all the ions are getting involved in the equilibrium, right? So please describe what kind of ion is getting involved in the chemical equilibrium in the next column. And then, just as the previous example, please describe the color and direction of the equilibrium shift, and please explain why the equilibrium shift is brought. In the stress 3, you put some tin chloride solution. This is kind of tricky, but please read this sentence. Tin 2 chloride has a tin 2 plus ion, and it's a reducing agent that reduces iron 3 plus ion into iron 2 plus ion. So in this case, iron 3 plus ion is removed from the equilibrium system, and as a result, the equilibrium will shift. Please explain the color change of the solution based on this experimental procedure. For the rest part is acid-base reaction. Based on the observation of the color of Kater, you will be able to explain what is happening during the experimental procedure. So that's it for the worksheet. Good luck.